It's really lovely to be here at ISTA. It's a great, great pleasure. I've been working with quality teams here in Sofia for more than 4 years now. Quite a few of the guys are in the room. One of my things that I was immediately struck by was the variety of excellent innovation around what we do in software testing. And it's great to be part of such a forum as this for exchanging all sorts of ideas and shaping the future of software quality and of software generally. I think we know how fast the world is changing, and there's an interesting debate I was just having with Hristo about, what's the future for engineers in a sense? When the machines do all the coding, what are we going to do? Well, that's an interesting one. It's not actually my topic for this afternoon. I should perhaps explain my role. It's a slightly unusual role. It makes perfect sense to me. It takes a little bit of a time to explain to anybody else. But I'm the head of both quality and projects. So if you know that thing at the end of a project where the project manager is saying, this thing's got to go live, and the quality guy is saying, this thing cannot go live, right? Well, in our organization, that debate, which occasionally I've seen actually descend to people throwing things at each other, takes place between here and here. So nobody else wastes any time on it. But it does also mean that I'm not just in my sort of role as actually watching a load of people do a lot of interesting stuff, but also from that perspective of my responsibilities, I'm looking very acutely as to the costs of everything that we do. And that's really the subject about what I'm going to talk today. So, which is about the business benefit of test automation. So, the abstract for this, when I put it together, was basically, we all know, it's obvious, it's blindingly obvious that we should automate tests. But when you actually sit down and try to explain to a finance guy why they should fund it, actually you try a few things and most of them don't work. So I just want to share with you how I eventually managed to make it stick. So to clarify a little bit in terms of context, right, there is an important asterisk there, right? I'm talking about product development. I'm not talking about individual projects. So individual projects which, when they're done and dusted, you forget about it, you won't move on to the next one. That's a totally different business case, and I'm just simply not going to go there. That was my old life. My new life is in products, and specifically, actually, which is somewhat relevant to the context and some of the things I'm going to say, B2B products. However, a lot of the sort of modeling that I'm putting here, it really wouldn't matter if it was B2C. But that's where I'm coming from. And the subtitle is How We Convinced Finance. And this is me. At the end of these, in the templates that the organizers kindly sent out, there's a lovely thing about, your Facebook, your LinkedIn, your Twitter thing. I have none of those. This is the only way to reach me. Actually, no, I am on LinkedIn, but anyway. Okay, so I think the first thing we've got to bear in mind, if we're talking to the finance guys, we've got to talk their language. And that's always money. So apologies to those of you who are very familiar with this concept of cost of quality. Bear with me while I explain it to the two people in the room who haven't come across it before. So really, cost of quality is a way of breaking down a project cost into two things. One is the cost of performance, and the other is cost of quality. Now, the cost of performance, this is what you want to spend your money on, right? When the guy says, please build me one of those, he thinks he's getting all of this lot. He's getting a product, he's probably getting some documentation around it. It's all totally wonderful. He knows that the requirements of the design have gone into all of that stuff, and that's great. And of course, we live in a perfect world. So this is all we need to do, right? We just sit down, we look at the requirements, we say, yeah, that's okay, here's a design, blah, 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 job done, push the thing out the door, move on to the next thing, right? That's the perfect world. I know you guys live in Sofia, right? Because nothing ever goes wrong. But what I can tell you is in the rest of the world, we have to worry about other things. So it's just possible that outside the borders of Bulgaria, there might be some developers who occasionally make a mistake. Or some designer who occasionally forgets a small but rather important part of the specification. So we need to sort of think about these things as well. As I say, obviously not in Bulgaria. So we divide the cost of quality into three things. The first one is prevention. This is the best way to spend the money that's not actually being spent on performance. Because this is the stuff that will actually make those developers better and produce fewer defects in the first case. So, you know, there's an English saying, an ounce of prevention is worth a pound of cure. Now, that's really difficult to translate into a country that's only ever used the metric system, but the ratio is 1 to 16. Okay, so you've read this while I've been talking. I'll move on to the next thing, which is where we spend a lot of our time in the testing and quality business. It's around actually looking, well, is this thing actually good or is it not good? And one of my particular bugbears, my sister used to work in the pharmaceutical industry. One of the things I struggle with in software is that we confuse quality assurance with quality control. Mostly what we do is quality control. We call ourselves QA, but actually it's control. We're seeing something and we're saying, is this okay? Does it meet its specification? Whereas quality assurance is, are we doing everything we need to do to build the thing right in the first time? Now, I know I'm not winning this battle of terminology in the software industry, so I'm just moving on from that thought and saying, basically, you want to do the prevention, which for me is the assurance. You have to do the control, which is the appraisal. And then the next thing is, of course, if you get this wrong, well, outside Bulgaria, you get all of this red stuff, right? Which is really bad. So the cheapest thing you can do is probably another review. You can do another test. You've probably got a defect to fix. And then you can see as you read down the list how much more horrible your life becomes, right? And this obviously depends a little bit, and I'm going to come back to this later, depends a little bit on what's the impact of the product you're making, who's using it, what happens if it doesn't work. I used to build spacecraft instruments before I moved into software. There, you have no opportunity for repair. And in 2000, I was in a room in one of NASA's centers, and we were waiting for the telemetry from Cassini to see whether we'd put a cover over a particular part that we'd built. And this was something I had literally designed in a bar. And we were just waiting to see whether this cover would come off and whether the temperature, if this came off correctly, the temperature was going to go down. And a bit like, I guess most of you have seen Apollo 13, you know, the movie. And at the end, they're waiting for the signal to come back, and it's late, and they're all biting their nails, and it's, you know, it's way beyond the time that anybody's ever done. This was late. And we thought, oh, that's it, it's completely broken. And then the temperature started to plummet. But the point is, there's absolutely nothing you can do about it in those circumstances. So there, your cost of failure is immense. You know, it's just, you can never recover from it. But think about it in the medical world, for example. You know, that's why I'm starting to mention things like lawsuits and insurance premiums. Most of us probably don't do this. On the other side, and I'll come back to this, think about a sort of free game app on a mobile phone. Well, you know, if it doesn't work, well, there's plenty more apps out there, right? So, okay, so cost of quality. I'm going to refer to this, so I do hope you've digested it, because I'm not actually going to show the slide again, right? But I'm just going to refer to the concepts. So, key thing is, it's a juggling act. In the non-perfect world outside Bulgaria, we need to make sure that we're spending enough on the prevention and appraisal so that the cost of failure doesn't overwhelm everything. Because what the people think they're really buying is the green stuff. right? So if we don't spend enough on prevention and appraisal, we get the failure, and then all of a sudden, as a proportion of the whole, the cost of performance starts dropping, right? So the art is, how do you set that? We could go and spend a fortune on prevention, and actually then we could have no failure whatsoever, but we've still actually overwhelmed the benefit we're getting in the cost of performance. So it is an art, it's not a science, and so on. But the colors are there for a reason. Green is good, red is bad, everything else is somewhere in between. Test automation comes in this tools bucket here in prevention, right? So what does it cost? Well, of course, like most things in life, it depends. One of the models that I find terribly useful, and anybody who's ever worked anywhere near me knows, because I bore them with it on a regular basis, is it's derived from the V model, which is terribly unfashionable these days. But the point about it is that actually your specification will always have to be decomposed. So you think about, somebody wants some massive great widget or some new system. They've got business requirements. Various other levels of requirements are derived down from that, down to the point where actually somebody could actually write some code. Now, the beauty of this for me is that then actually you sort of think, well, how do we check that that actually went okay? And those validation levels correspond to the specification levels that we've got, right? So you can see me clicking these up as they go. And clearly, you've got a problem if actually what you're doing at the sort of detailed design or the coding level is something that requires an integration test to validate, right? You're probably getting it wrong and doing things more expensive than they need to be. And obviously, the other thing is you'll tend to have, at the top of this thing, you'll have a few big things, both on the requirements side, the specification side, and the validation side. And at the bottom, you'll have a lot of very small things, both in terms of the code changes that you're doing and on the unit tests that you actually do to prove that they worked. So let's look at the costing. So I think you sort of, at the unit test level, it's probably about the price of a skateboard, something like that. When you've factored all of the things in, something like that. This, and I'm going to come back to this, if you don't know what this is, and it certainly will, this is the Tata Nano. The story of which car is very interesting. It was deliberately designed, and in fact, the head of Tata challenged the guys to come up with a car that could be sold for 1 lakh. And 1 lakh is 100,000 rupees, or basically a little bit more than $1,000. And he did that because he saw, as anybody who's been to India will have seen, a family of 5 on a motorbike. And I've seen them with televisions as well, and I don't mean flat screen ones. I mean like 26-inch CRTs. And so he challenged them to come up with an affordable car for that segment of the thing. So that's, more or less $1,000. Well, I mentioned that as you go up the chain, things to get a little bit bigger, a little bit more expensive. So maybe it's a Fiat 500 at some level. And who knows, depending on what you're doing, maybe you need a Ferrari at the top. I don't know. As I say, it depends. But clearly there's some sort of thing there, which is why you really want to make sure you're not doing the integration tests to check one method in some Java class. Okay, what happens next? Oh, sorry, I missed a point. I've highlighted this point, the Tata Nano, not just because I actually quite like the story, but actually because that's where I spend most of my life. In reality, because the way that we're organized, the unit tests sort of sit mostly with the development team, and I just watch them go past. And I'm going to come back to that in a minute. But the majority of the tests that we deal with are ones that have got some sort of scripting behind them, and so on. And they pretty much cost about that sort of thing to automate. So let's think about the cost of running these things manually and just work out how we're going to convince the finance guys that it's a good idea to automate them. Well, I reckon, and I realized this morning as I was looking through these slides, I should have put this on a slide by itself. I reckon it's about $50 for the sort of tests at that level that I just described. Something like that. It varies, obviously, because they're different shapes, different sizes. Some people can test faster, some people can test slower. But if I look across the sort of stuff that we do, it's more or less $50. So now we've got a problem, because we've got a $50 test case that costs $1,000 to automate. So it breaks even once you've done it 20 times, right? And the interesting thing about that is that if you, and I'll come back to sort of some of the logic around it, but if you're running releases every 9 months, as we used to, right? So 20 times 9 months, that's about 15 years. Even if you drop that to 6 months, it's about 10 years. The other thing is that actually, what's quite interesting is, and I've been to India a lot, which is why I know about that car. I don't know about Bulgaria, but in England, the roads are swept by big machines that have big whirly brushes on them. In India, the roads are swept by people, because the cost of automation is not worth it, right? It's also a good way of employing people. It's not a very nice job, but hey. So far we've got a problem, because when I was a bit younger than I am now, the finance guys basically, you could just about convince them if things were 3 years or less on return on investment. And it's kind of hard the longer after it is. And nowadays I think people are even more impatient than that. So then you sort of think, well, I thought, because I was trying to figure this out, but what about the fact that if a defect escapes, it's a lot more expensive to fix? Does that actually help us? So let's look at that case. So one could have an arbitrary, elaborate model about all of this stuff, but let's look through this one. So we start out by executing a test, and that costs us $50. So we've then got a decision. Did we find a defect, or did we not find a defect? So again, when I went through this morning, I realized I'd done this the wrong way up. So I'm going to ask you to look at the bottom part first. So let's say we did find a defect, and let's say that happens 2% of the time, right? Well, then somebody's got to fix it. That's probably $500, right? Something like that. We're then going to retest it. So we've paid $600 for 2% of the test cases we execute. Take the next path up, right? So we didn't find a defect in our initial test. Hooray. Or hooray if you're a developer. Yahoo sucks if you're a tester. And then, but somebody downstream did detect the defect. Well, now this is really embarrassing, right? And let's say that 10% of the things that happen in that case, actually there was a defect detected. That's, defect removal efficiency about 90%, something like that. Seems about right. Okay, so now the defect has escaped. So it's 5 times more expensive to fix, because you've got all sorts of people involved that you never knew existed before this point. So let's say that the cost of fixing it has gone from $500 to $2,500. Oh, and then we've got to test it again, so there's another 50. So overall, we've spent now $2,600 for just less than 10% of these test cases. Now then there's the top path, right? The top path, well, we didn't find it, and actually nobody else found it either, which either meant that everything was fine or nobody cares, right? So fine. In this case, all we spent was the $50, and that happens 88% of the time. Okay, so quickly doing the maths. Our expected cost of this is about $310. Okay, so now let's put the automation in. This looks more promising, right? Because we started out by saying it costs $50, and all of a sudden we got $300. Yeah. But if we automate, yes, the test execution goes down to 0, but everything else pretty much stays the same. And our expected cost is now $247. So what we've got to look at is what's the difference between these two numbers, like not what's the absolute number in either case. So it's looking a bit better, right? Previously, we were looking at 20 iterations of releases. Now we're looking at 15.6. It still isn't going to convince the guys. If we're talking about 6-month release, it's still 7.5 years. So I couldn't, with a straight face, go to the finance guys and say, give me a load of money for a load of test automation on the basis of this. But then clearly we've got something going on about the release interval. So maybe that helps. Are we getting somewhere with this? And a brief digression that sort of says why this might be relevant, right? So I think we're all seeing release intervals accelerating. Customers are more than ever sensitive to time to market. Demand for cloud services now is outstripping that for on-premise software. And here's, for me, one of the sort of killers. The security threats we're getting are growing at an exponential rate. And if you put that in combination with the other factor that I've put in here, and this is from 2013, this guy reckons that 90% of the code in applications is not actually written by the person who wrote the application, right? Which means, actually, you've got an awful lot of dependencies outside, and anybody could find a security flaw in any of them, and that's all right. You don't have to scratch your head about what you're going to do about this flaw. You just need to upgrade the library. And then, of course, you've got to check that nothing else broke when you did it. And the point is, for your customers, you've got to get that secure thing out to them. And if that's happening sort of in a real-time thing, they probably can't wait 6 months for a really severe security thing. So I think all of these things are causing us to accelerate our release cycles. So we've got to release faster. And the finite guys do get this point. But there's a little bit more. We've started this analysis by thinking, here's a test case. I've got to do the test case, right? There's another one. I've got, how many? I think the later modeling that I've got is about, 12,000 test cases is roughly the sort of library that we're running, right? So, you've got to do these 12,000 things. But testing is not the thing we want to do, right? What we're really here to do is to control the risk as part of an overall value chain. It's there to measure and control the risk to our customers of using our software, or even to ourselves if we're consuming our own thing, right? So think about it from another point of view. Let's not think about it from the point of view of the tests, but think about it from the point of view of the defects that we're trying to not be there, right? So there's two sides to this. Coming back to the non-perfect world outside Bulgaria, right? How many defects are likely to be introduced? So that's what I call defect injection rate. And how many escaped defects are acceptable? And the thing to do here is to set a budget. Now, of course, in some situations, that budget is 0. For me, in my past life, it was 0. Right? In medical situations, for medical applications, for particular types of things, it is 0, right? And you've really got to be very, very thorough on this. But to be honest, think about the other example I gave around some sort of game. Well, actually, it's probably a lot more. You can be a lot more lenient on what you actually need to happen. And certainly I expect that most of you do, certainly we do, classify defects by severity. We also classify our test cases according to the severity of the defect they're intended to catch. So yeah, we'd sort of say severity 1, or blockers, well, you can't have any of those. Mediums, yeah, there's probably some reasonable budget of those. And minors, well, Another English saying, there's a sort of one of these rhymes that you learn at school, which is, this year, next year, sometime never, right? Which is what you do. Maybe there's something similar in Bulgaria, right? But if you're eating plums and they have the stones and you put them around the thing, and it's so this. The other one is Tinker, tailor, soldier, sailor, rich man, poor man, beggar man, thief. So that's who you're going to marry, and then this year, next year, sometime never is when your marriage is going to be, right? So it's similar for severities of defects. Blocker, you really ought to fix this year. And a major you probably ought to fix next year, and a medium sometime, and a minor, well, never, right? By the way, if those are your SLAs, you probably need to have a word with somebody, but yeah, is the point. So the thing is that you can be more relaxed about your budget for the lower severity defects that you might find. And this is actually helpful. So I think I've covered a lot of this. So what's the cost of failure for that defect? So I've given you the example there already. Can you fix it afterwards? And if you can fix it afterwards, how many of those things can you afford to fix before the next one turns up? Or are you continually running around sort of patching things up and you just end up chasing your tail? How long does it take to create, propagate, and apply the fixes? So if you've got a time criticality around it, then actually, and you've got a really short time, if a defect appears before you need to resolve it in production, then actually you're probably less tolerant about the number of defects that you have. And then finally, how good's our test coverage, right? If actually we're only got 50% of our overall sort of functionality covered with tests, probably the other 50% that's not covered is all going to consume your defect budget, right? And I'm going to come back to that. Now, you've probably read the thing at the bottom, which is allegedly a Russian proverb. A certain number of fleas is good for a dog, otherwise it forgets it's a dog. So in the early days of electric light bulbs, I think by about 1910, they'd worked out how to make a light bulb that would last pretty much forever, right? Now we have LED bulbs and they last pretty much forever, but actually since 1910 this has been possible. And the reason why Philips became such a successful company was because they actually worked out how to make light bulbs, but they weren't very good. But they managed to convince the Tsar to get the monopoly of light bulbs in Russia. And so Russia was flooded with these rather short-lived Philips light bulbs, and the company grew on the basis of this. And actually, if you think about built-in obsolescence, and even the slightly better light bulb manufacturers than than Philips, then actually what they're doing is, the fact that the thing burns out every so often means you go and buy another one, right? So this is really the meaning behind a certain number of fleas is good for a dog, right? Otherwise it forgets it's a dog. But perhaps a better summary of this whole thing is perfect is the enemy of good enough. And if you think back to the cost of quality discussion, if we went for perfect, then the cost of prevention would be very, very large. And that would not be balanced against the cost of performance, which is where we actually want things to do. So with all of those in mind, the various factors, including a budget that we have around all this stuff, the defect injection rate, and so on. What is the effect of the release frequency or the release interval? It's, in the end, relatively straightforward to model, once you realize that that's what you do want to model. And the sort of parameters in terms of what you see on this graph are as follows. I think the missing one is that I think there's about 12,000 test cases here. But we've got a team of 100 developers. Every 1,000 coding hours, they create 20 defects. That's my preferred measure of defect injection rate. I was introduced to it about 20 years ago. The nice thing about it is it's pretty much agnostic to technology. It's pretty much agnostic to whether it's new code or incremental code changes to existing. So 20 is a sort of, moderate average. I've seen 50 and I've seen 2. 2 is very unusual. Less than 10 is good, right? Another assumption, coding is 25% of development time. We've got to think about things like the design, the analysis that precedes the design, and things like upskilling, all of those sort of things. Same assumptions on cost as I said before. Test is continuous rather than at a separate later stage. So It's slightly harder to model when you do the sort of model the test at the end of a release cycle for a defined period of time. And if you sort of think about what happens in an automated sense, you're running it all the time anyway. It doesn't actually make a heap of difference. But so that's just a note for you. The defect budget. So it's probably better to do the bottom one first. So I've assumed that 20% of the defects that the developers put in are actually relevant to the budget. Like if my budget is just on majors or severity 2s, then that's roughly 1 in 5 of the defects they put in, and I'm allowing myself 4 of these per year. Okay, so start at the top with the blue curve. This is what happens when everything is manual. So if you start at the right, you see 120 working days. That's six-month release interval. And you can see the costs of actually executing that lot to get the coverage you need to meet your defect budget there. And that's a fairly hairy number, but that's just what the thing sort of pulls out. And obviously, as you try and increase your release frequency, let's say we go down to 60 working days and 3 months. Well, look, these arrows are the same size. Why have I done that? Because actually, one of the things about curves like this is they create optical illusions, and you think things are different sizes when they're the same size. The cost has doubled, right? And if we were to go faster again in response to all of the things I said before, actually it's quadrupled. So now you're having a very different conversation with the finance guys. You're basically saying, we know it's really important to release faster, and now instead of what's on this graph, 600,000 every year, I now need 2 million. And all of a sudden, he or she is beginning to get the point about what you're talking about, because you've moved it away from, here's a thing I want to do, and I can do it manually, or I can do it automatically, but to automate it is going to cost 20 times what it costs me to do this. Because you've moved the focus from the cost of doing that automation to the cost of not doing it. And you've moved it in the cost of quality thing from the cost of performance to the cost of failure. And that's much more compelling as a reason. So what you see here is, this is, now you've understood the graph, you can sort of see, obviously, the more automated we are, we've only got the manual test to do, that's a lot cheaper. And of course, as we start on our thing at the bottom, you can see the 90% automated curve, the bottom one there. Of course, in the situation where we've got the 6-month release cycle, it's 1/10 of our original cost. But as you increase it further, the effect of 2 things really comes into play that I'm going to show on the next slide. So, let me do this. So the first thing is, this is just a smaller version of the same graph that you saw. And compare this with what happens if our developers are more perfect. And they're only introducing 5 defects per 1,000 coding hours. Now, what we see here is that, and this is what this arrow is showing, actually that 90% automated curve has got a lot closer to the origin, right? So the reason for that is because there are fewer defects being injected, actually I've got a lot more confidence that I'm going to hit my defect budget, right, within that defect budget. And that's illustrated even more if I increase the defect budget. Because now I'm getting to the point where, and you can see on this one that I've just shown, actually that 90% curve is completely against the horizontal axis. And if I do both of these things, then actually you only see half the curves anyway. Why? Because I'm entirely confident that actually with the automation coverage I've now got, the developers can't introduce the bugs fast enough for me to need to do the manual testing to find them. And I said I'd come back to unit tests when I was showing you the V-model thing earlier. It's not uncommon to have criteria, which may even be set in the, in the build process of around 50 or 60% unit test coverage. This is not uncommon. My observation is, if you think about, as I say, I inhabit that next level up, at that level, I can't remove one single test case. But if the unit test starts getting up to 90, 95, maybe I'm more confident. And a similar thing is happening here. When the automation is getting up to a very high level, actually, I'm confident I've got the coverage that I actually need, that I will meet my defect budget. And I don't need to do anything like so much manual tests. So I can meet this, in this scenario, with, what's that? That looks like about, in the bottom right scenario, 60%. And even if I don't change my budget, right, then 90%, actually, I'm doing a very minimal, I'm doing a tenth of the effort that I previously was. And look, by comparison, I am roughly, even if I go down to 1 month releases or even perhaps 2 weekly releases, I'm still spending less than half of what I was annually in terms of manual test effort. So, did that convince the finance guys? Well, yes, it did. We got a project funded to have an external partner to automate our historic test cases. We realized we would never be able to do that by ourselves. It wasn't zero-sum because we had to actually check everything that they were doing. You've got to test the tests, if you see what I mean. And I'll come back to that in a minute. So there was a lot of stuff around that. The other thing is we basically invested in our own future, so we required all new test cases to be automated. So we started with 50%, we increased that to 80%, and now actually anybody in my team who says, I don't want to automate this test case, has to come and see me, and it's not a very pleasant conversation. So we've also, in the middle of all of that, because of that investment that we've got in there and our own investment, particularly actually in the test automation, we've got a test platform that we've rolled up at the higher levels up the V model, and we're using it routinely for that. So not just at the product level, but also including the configuration. I'm not going to tell you about that because there are people in this room who will do a much, much better job. It's a totally different story. But it's all good. So is finance happy now? Yes. And that was even before we accelerated the releases. And I'll show you this graph to sort of demonstrate it. So what you're seeing here is, from left to right, some of the recent releases we've done, and the numbers in brackets are the number of months that they sort of represent. The size of the bars is actually the number of test cases that we executed in release testing for that thing. The blue and the turquoise lines are our levels, percentage levels of automation. So the top one is for priority 1 and priority 2 test cases, and the turquoise one is for priority 1, 2, and 3 test cases, which, as I said earlier, correspond to severity 1, 2, and 3 defects. So you see we're now sort of 90%-ish on the P1 and 2 and about 60% on P3. We've still got quite a lot more of the historic stuff to do. But the really interesting thing, and the reason why the finance guys love us, is the green curve. So the cost of our release testing in units, which for obvious reasons I can't actually share outside the company, but so these are arbitrary currency units. This is a real graph. It's just that I've hidden the actual numbers. But you can see we're about, well, a third or a quarter of what we were previously spending on this stuff. So we're happy too. We got more test coverage. We got shorter release test. We've stopped calling it regression test because that happens earlier. We're finding defects earlier. We're releasing faster. You can see in terms of the timescales. And actually, we're going even faster than that now. And our customers are happy too. So what else did we learn? Or what did we learn along the way? First of all, it's a lot easier to put in automation as you write test cases than try to do it afterwards. It's a lot easier. But you need help for the old ones. And as we did that, we found we didn't like most of our tests. Quite a lot were written as if the only person who would execute them was the person who wrote them. There are very similar statements around code. But the same thing is true for tests, even then they're just written out on paper. We had a lot of tests that were at the wrong level that we needed to split up. And we had a lot with missing metadata. So there's a big cleanup that needed to go with it. Other things. You need a really solid CI/CD pipeline. Analysis of the test failures is onerous, and there's a huge learning curve. So this graph here shows what happened. These are, as each batch came in from our external partner, the vertical axis is the percentage of those test cases in the batch that we thought were first time right. And you can see by any of the measures, and it doesn't really matter which the three curves are, you can see it took them a year, really, before they'd got to a consistent level, sort of up in the 90% as far as that stuff is concerned. So, a lot of people will think a learning curve is of that sort of 6 months, a year thing. This was actually a measurement of it. It's quite interesting to do internally as well. Prevention is better than cure, right? I mentioned this before. Reducing the defect injection rate, you saw it on the graph, actually makes the automation case even more compelling. The other thing we do now, which we learned to do, is we celebrate when the automated test finds a defect, particularly if it's a really big, hairy one. And we really like that, because after all, a test case that didn't actually find a defect, what is its purpose in life, right? So it's slightly pointless. And that is the end of what I have. So, in summary, basically, the key thing is to, in terms of convincing the finance guys, number one, talk their language. Number two, don't just look at it from a point of view as there is a test case to be automated. Look at it as there is a risk to be controlled. And then concentrate on the cost of failure rather than the cost of performance. Thank you.